Okay, we're continuing our review, and we're up to number 11. Find the end behavior. End behavior means the limit as x goes to infinity and the limit as x goes to minus infinity. All right, so if we look at A, and we remember that the end behavior is only influenced by the dominant term in the numerator and the denominator. So what's the dominant term here? Well, let's see. Over here we have the dominant term is x to the fifth. That's the term with the highest exponent in the numerator, and in the denominator we have minus 2x squared. All right, so that's all we have to look at, or all we have to consider. Okay, so here we go. We'll take the limit as x goes to infinity of x to the fifth divided by minus 2x squared, and just reduce that. Reduce it, and that's the limit as x goes to infinity of x cubed over minus 2. So as x goes to infinity, x cubed goes to infinity, and since we're dividing by a negative, we have the limit as being the limit is equal to minus infinity. And now if we take the limit as x goes to minus infinity of the same quotient of dominant terms, all right, so that's the limit as x goes to minus infinity of x cubed over minus 2. So if we substitute in negative values of large magnitude and cube, we get something negative of large magnitude, and we're dividing by a negative, and so negative divided by negative is positive, so the limit would be positive infinity as x goes to minus infinity. Okay, let's look at B. All right, so here we have the dominant term on top is square root x, and the dominant term in the denominator is the square root of x squared. Keep that square root on there. All right, so let's look at that. So we have the limit as x goes to infinity of square root x divided by square root x squared. Okay, or limit as x goes to infinity. Square root x over x squared, that's 1 over x. Reduce that, and we have 1 over the square root of 1 over x, or 1 over the square root of x. As x goes to infinity, the square root of x goes to infinity. So this limit is 0. And now notice that the domain of this function is x greater than 0 because we have a square root x over here. So we're not going to take the limit as x goes to minus infinity. All right, so let's just write the domain here. The domain is x greater than 0. All right, let's look at C. Okay, so I'm just going to pick off the dominant terms again. And on top we have 7x to the fifth. And then the denominator 3x to the fifth. So notice the power of x is the same on top and bottom. So that limit is equal to 7/3. And we'll have the same as x goes to minus infinity. All right, so this would be this situation, and the one above where the limit was 0 determines a horizontal asymptote. So here we have a horizontal asymptote. At y equal minus 3. Sorry, at y equals 7 over 3. At y equals 7 over 3. All right, let's look at D. doing the limit as x goes to infinity of minus 3x to the 16. That's the dominant term. Okay. So x to the 16 will go to infinity, and because of the negative in front, this limit is minus infinity. And as x goes to minus infinity, when we raise a negative number to the exponent 16, we have something positive. So this power of x will go to positive infinity, and because of the negative sign in front, again, the limit is minus infinity. So that determines the end behavior. Okay, we'll continue with 12a. We're doing some graphing. Okay, so first we're going to get information from f of x. And let's start with x-intercepts. So since this is factored, it's easier to see where it's equal to 0. All right, so f of x is equal to 0 when x is equal to 0, minus 2, and 2. So those are the x-intercepts. And the y-intercept is 0, 0. Okay, let's talk about end behavior. Well, the leading term here is x to the 4th. And as x goes to infinity, x to the 4th goes to infinity. And as x goes to minus infinity, x to the 4th also goes to positive infinity. So the limit as x goes to plus and minus infinity is equal to infinity. All right, now let's talk about, let's get information from f prime of x. Okay, so f prime of x, we take the unfactored form of f of x and differentiate, and we have 4x cubed minus 8x. Let's factor out a 4x, and here we're left with x squared minus 2. Okay, or x squared minus 2 we'll write as x minus square root 2, x plus square root 2. Alright, and we want to know where is this 0, and we'll put those on the number line. So we can see that this is 0 at x equals 0, root 2, and minus root 2. So those go on the number line. All critical values. Alright, to the right, plug in something like 10, for example, and everything's positive. In between, let's say we plug in a 1, and this is negative, this is positive, positive, so that's negative. We plug in minus 1, we have this is negative, negative, positive, so that would be positive. And something to the left here, like minus 2, would make everything negative. 3 negatives is, the product of 3 negatives is negative. So we know that the function is decreasing here, increasing, decreasing, increasing, and we see this is local min, max, min. Alright, so we have a min, a max, and a min. And if we substitute minus square root 2 into our original function, we have to substitute back here. Okay. Alright, so if we substitute the square root of 2 back in, we get, for a minimum, we have minus 4, a y value of minus 4, and the max occurs at 0, 0, and the second minimum occurs at square root 2, also minus 4. So let me emphasize, this was obtained from substituting into f, into the original function. Alright, let's get information now from f double prime. I'll just underline that, f double prime we're working with now. All right, let's see, what was f prime? It's easiest to take the derivative of this expression, the unfactored form. All right, so that would be 12x squared minus 8. All right, and we could just factor out the 4. We want to know when is this 0, so set this equal to 0. And we have, let's see, 3x squared minus 2 equals 0. And that leads us to x squared equal 2/3, or x is equal to plus or minus the square root of 2/3. So we do our plus minus analysis for f double prime. And substituting in values, we get positive, negative, positive. So here the graph is concave up, and here's down, and here's up. And we have 2 inflection points. Substituting back into the original function, we have minus 20 over 9 for the y value. So now we can put that information together. And here's what we have. Okay, we had 0 was an intercept, an x-intercept. Okay, this is the x-axis, and so 2 and minus 2. Okay, those are all intercepts. And now let's put in the max-min. So we have square root of 2 minus 4. Okay, I'm going to not draw this to scale. Let me put the minus 4 here. Okay, square root of 2 minus 4 and minus square root of 2 minus 4. So those are both minimums. So draw them as minimums. And 0, 0 is a maximum, so draw that as a maximum. All right, and then we have end behavior I didn't put in. We have going to infinity on the right and left. All right, now we have this inflection point, 2 inflection points at square root of 2/3 and minus square root of 2/3. And over here at y value minus 20 over 9. And notice that does seem to fit in. Minus 20 over 9 is just a little bit smaller than minus 2. So it's almost halfway between here. So that does seem to look right. Okay, so here we have switching point in here. Here this is concave down. And now concave up. And this is the intercept, so let's make sure we go through the y-axis at that point. Okay. So that should be minus 2. And here we have the curve switching from concave down to concave up right there. All right, and that's pretty much the graph.